All right, we're starting in on the cardiovascular system this week. Welcome. I'll show you. Well, it's just dusk right now, and we are wrapping up the penultimate week. So in track and field and high jump, the penultimate step is the second to last. Penultimate. One of my favorite words. So second to last week, we have quite a bit to do still, which is really fun. This lab I think is going to be really neat. If you think about your heart, as a lot of people think that's like where your soul originates from, maybe that's like where you emanate love. So we're going to dive into really like physiologically or what the function of the heart is, and also look at the structure that allows that function to take place. So the anatomy basically of the heart. And earlier this week, I went to Arches, so I'll share some of those pictures with you. Maybe I'll do that right now, actually. Okay, and you can actually watch that as an intro. I'll make a separate video that's an intro to these lessons, but I'll try to keep this pretty to the point. Moving through the Smart Sparrow. This one in particular, you needed to load. This is the change of heart we're about to do. You needed to go to modules. I just loaded it, so we'll see if it loads again. But when you go into a change of heart, it's an auxiliary lesson, supplementary, so you have to load it here in this new window. All right, and here we are. So let's get started. We're going to learn, how does the heart deliver oxygen to the body? What impact does space flight have on the heart? And how can the effects of microgravity on the heart be counteracted? Let's go ahead and start the lesson. Making a trip out to Mars is no walk in the park. There are dozens of tasks that need to be accomplished while on board your flight, and more once you land on the red planet. Completing tasks such as constructing a base on Mars, carrying out research, or just keeping oneself alive requires astronauts to be in peak physical condition. The question is, will they be ready once they land? In this lesson, you'll explore that very question. Will the astronauts on your mission be physically able to survive and complete their mission on Mars? To learn more about how your body manages physical demanding tasks, select a physical activity that you would most likely find yourself doing. Running, yard work, dancing, lifting weights, walking to school, playing sports. Most likely, I'd do a mix of all those things. So go ahead and, I guess I gotta choose one. I wish I could, this looks like a really cool yoga pose. Wish I could do that. Actually, I think I might be able to. Go ahead and try. I really do love dancing though. I think everybody should dance just as a break. We'll take a dance break during our live lesson. That'll be really fun. Okay, feeling the burn, making a trip out to Mars. Okay, we already heard that. Now imagine you are knee-deep in this activity. You have exerted yourself for almost an hour. How would this make you feel? Okay, would you be hot, sweaty, tired, heavy breathing, heart rate beating fast, or would you have pain? Sometimes Smart Sparrow has some interesting choice of, okay, anyway, maybe I would have, my heart would be beating fast. And I'm gonna go with that. You're probably feeling hot, sense your heart racing, and maybe even a slight hint of exhaustion. While you're hard at work, so are the organs inside your body. By lifting the hood on what's going on inside the body during intense physical activity, we can see what organs are in play during such tasks. We can then check the same organs in astronauts to see if there's any change that may prevent them from completing physically demanding work. Predict what you think is going on inside your body during vigorous exercise. Is it that your muscles are working harder? More blood is circulating to your brain and muscles? Is it that the pathway signal to your brain to cause you to breathe more rapidly? Maybe. Is your heart pumping more rapidly? Very perceptive. We're absolutely right. In fact, all of the effects you've seen above can occur when the body is pushed to complete a rigorous activity. Let's hone in on one of these effects. All right, getting into the weeds here, tracing the path. To find out what's going on inside your body during intense physical activity, let's start with a basic fact you outlined earlier. Your muscles work harder during intense physical activity. Muscles can obtain energy from a number of sources. During long periods of intense physical activity, your muscles need a stable supply of oxygen and a fuel source like glucose. As you learned in the previous lesson, these molecules are transported via the blood. But how does blood rich in oxygen and glucose reach the muscles cells that need them? Okay, so here we go. Now what we're looking for is how blood actually gets to the rest of your body, the ones that are rich in oxygen. So we see here on our diagram the right side, which is really the left side of the body. If you were to like transpose yourself, that's how a lot of anatomy is displayed. It is red, that's oxygen rich, that's being pumped out of the left ventricle up into what's called the aorta through the systemic circuit to the whole body. So blood leaving the left side of the heart is rich in oxygen and supplies all the major organs of the body with blood. All right, when we pump out blood, the systemic circulation is the way in which your oxygen-rich blood can be pumped from your heart to almost all major organs of the body, including your muscles. The heart is able to pump out blood by beating. A single heartbeat, or the cardiac cycle, has 3 phases: diastole, systole, and the pause in between. I've heard this said systole or systole is when the heart contracts and blood is pumped out of the heart's ventricles, and those are the bottom portions. I remember it because it looks like a V. So systole, you can see it's moving in. Diastole is the in-between, when the heart is filling with blood. Use the diagram below to locate the chambers of the heart that pumps oxygen-rich blood during systole. Place the dot on the correct location. Okay, so that's going to happen in the ventricles. And let's see make sure pumps oxygen-rich blood. So that's the left ventricle. See, it's like received by the atrium. And atrium really does mean like holding zone, holding cell. So it moves in through the atrium, into the ventricle, out through the aorta to the rest of the body. All right, cardiac output. For oxygen-rich blood to be transported to the body's major organs, including your muscles, it must be pumped out of the left ventricle. The amount of blood that leaves the heart's left ventricle each minute to supply these organs is known as cardiac output. Based on the evidence to the right, do you think there is a relationship between cardiac output and intense physical activity? Here we might notice that as the intensity increases, the cardiac output increases as well. And I would say that was this one. So we call this a direct relationship between exercise intensity and the amount of blood your heart pumps. This makes sense. As your muscles work harder, the oxygen and fuels need to be delivered. To meet this increased demand, one of the things your circulatory system does is increase cardiac output. And that's a fancy word that just means your heart is pumping more blood. Increased cardiac output allows more blood, therefore oxygen to reach cells, which allows humans both on Earth and in space to complete physically demanding tasks. Exercise typically increases the demand for oxygen by cells. How would you decrease in cardiac output affect one's exercise capacity? So if we have less cardiac output, are we able to exercise as much? Probably not. But there's an intermediate here. So if this goes down, oxygen delivery is going to go down, and cardiac capacity is going to go down. So I'm going to scan through here. Oxygen delivery would decrease, and the ability to do rigorous exercise would decline. Both of those go down. And it says, good job using your knowledge to make an inference here. If cardiac output, or the amount of blood pumped out of the heart per minute, were to decrease, so would the delivery of oxygen throughout the body, assuming all else is equal. Without an adequate amount of oxygen circulating through the body, it will be harder to supply the muscles which require more oxygen during physically demanding activity. Cardiac output is the measure of how much blood volume is pumped out of the heart per minute. To find out what can affect cardiac output, take a look at the two water balloons shown here. If both are full of water, which will have a greater output, which one? These balloons look really similar to me. I think this one's supposed to be bigger. Oh yeah. So the balloon on the left is larger, so it can hold more water. So if you have more volume, can pump more blood. One of the factors that can affect how much blood the heart can pump per contraction is how much volume fills it in the first place. The more blood that fills the heart, the more it can pump out per stroke. The heart holds the greatest volume of blood at the end of its filling phase, called the diastole. The maximum amount of blood that the heart's ventricles can hold is called the end diastolic volume. What do you notice about the maximum amount of blood filling the left ventricles of the hearts after 12 weeks of space flight? We have a decrease over time in the amount of actual blood that's being able to fill the heart. And I would say here's the best answer. The maximum volume of blood filling the heart's ventricles is lower after 12 weeks in space. According to evidence on the page, the end diastolic volume decreases the longer astronauts are in space. That means that the maximum amount of blood a heart's ventricle can hold decreases after 12 weeks in space. So why does it decrease? Turns out, spaceflight can cause astronauts to experience a decrease in blood volume. The less volume of blood that is circulating in the body, the less can fill the heart. Therefore, the maximum amount of blood filling the heart decreases. Does the evidence in the graph shown right support the ideas that blood volume decreases in microgravity? I would say yes. Blood volume here decreases, and then here change in blood plasma volume during a longer duration decreased more. I would agree as well. Here it says, interestingly, astronauts in long duration missions do not lose as much blood plasma as those on short duration. Oh yeah, I didn't really read that right. Short duration is longer than long duration. This could be due to a difference in sample size or suggest that the body can readjust itself to accommodate the change. Interesting, because here you see n, the sample size is 29. Otherwise here n is 5. A heartfelt response. Like other muscles in your body, the heart can adapt to the load put on it. The muscles of the heart respond to the load or volume they have to bear. For example, the greater the volume of blood that fills the heart's ventricles, shown as end diastolic volume, the more heart muscles have to stretch to accommodate. Since heart muscles can respond to loading, this increased tension signals the heart muscles to contract harder. In the case of astronauts, less blood fills the heart's left ventricle. Make an inference about how you think the heart will respond. So here's my guess: the heart will not have to contract as hard. If you have less blood here, you have less need to pump more blood out. So let's see. Kind of seems like, losing muscle mass. If you don't have as much force, your muscles are going to decrease or atrophy. And here it says, the heart, like other muscles in your body, is affected by the amount of loading placed on it. The evidence to the right was gathered from 8 astronauts who were sent on a short duration mission into outer space. Use the evidence shown to explain how a reduction in the volume of blood filling the ventricles could impact the structure of the ventricles. So there is Alright, if we look at this graph, we're looking at mass, pre-flight versus landing day. decrease, one is higher than the other, of astronauts' left ventricle. The one that would actually pump all the oxygenated blood all the way to the body. The reduction of this left ventricle mass was the result of losing muscle in that area. And that's called cardiac atrophy. Predict how changes to the left ventricle might affect the body's ability to supply cells with oxygen and nutrients. So if we have less fluid filling the heart's ventricles, we have lower strength of contraction, decreasing the left side of the ventricle, decreasing cardiac output, decreasing oxygen delivery, which decreases the amount of exercise you're capable of. To summarize, in microgravity, the volume of blood in the body decreases, which reduces the amount of blood entering the heart. With less volume filling the heart does not have to contract as hard. This reduction in usage causes the heart to atrophy. This atrophy causes a reduction in cardiac output, which reduces the oxygen delivery to the body. With less oxygen to supply the tissues of the body, such as muscles, the ability of astronauts to carry out rigorous activities can be compromised. I'm going to go ahead and jot that down real quick in my notes. Cool. All right, so interesting to note, this is my ultimate page of my notes. I have no more space for notes, so I'm glad that this semester's coming to an end, although I'm sad to leave all you guys. So change of heart, blood volume down, blood fluid in left ventricle, which is the thing that pumps O2 through the systematic side of the heart. That leads to decreased cardiac output, which is the blood per minute, which leads to decreased oxygen to the body, which leads to decreased amount of ability to do exercise, which we are defining as cardiovascular deconditioning. And I'm going to write that one down. Cardiovascular deconditioning. So, heart is getting less good at pumping blood to the body. During exercise, oxygen needs to be quickly delivered to cells. Heart beats faster and increases the cardiac output. As cardiac muscles atrophy or decrease, I'm going to write that word down too, atrophy, the heart's ability to pump blood and oxygen throughout the body becomes impaired. This can be a problem for astronauts who have to work on Mars. This slows the capacity of the cardiovascular system, mostly the heart. This is referred to as cardiovascular deconditioning. Cardiovascular deconditioning can occur as a result of not being active. What type of person might also experience cardiovascular deconditioning? Probably someone on bed rest. That seems about accurate. Oh yeah, that is, okay, I skipped over this. But that's the one I want to choose. Uh-oh, now we're glitching. Oh yeah, this just kind of brings up those space experiments that we were talking about in the live lesson. Let me pull. So yeah, I wanted to share this. The NVHAB in Cologne, Germany. So they place them on strict bed rest to see what the effects of weightlessness are on the body. And also to examine carbon dioxide exposure to artificial gravity. Oh yeah, reliable air filtration. That seems important. All right, back to the lesson. In addition, to designing a countermeasure. So yeah, in the same way that you'd measure what the effect is, you want to also test how do we counteract that. So to condition the heart to respond effectively to the increased physical demand of a mission to Mars, cardiac atrophy needs to be prevented. What might you do to prevent your heart from atrophying from disuse? Take a look at the evidence gathered by 3 interns. Choose which of the following would be most effective. Salt consumption. According to the Mayo Clinic, keeping one's sodium below 2,300 milligrams can reduce blood pressure. A reduction in blood pressure can be helpful for preventing damage to one's artery. And I always need to think about blood pressure, the pressure of the volume within your blood vessels. So if you have less sodium, you have less stuff, which means you have less pressure, less little things pressing up against your vessels, less damage. But we're trying to prevent the loss of cardiac tissue. I don't know if that will necessarily help. Going nuts. According to an article, eating nuts 4 times a week can reduce the risk of coronary artery disease by 37%, also known as CAD. It's the lead cause of death in men and women. It occurs when arteries around the heart get clogged or narrowed by fatty deposits. Also bad, but that doesn't, again, reduce loss of cardiac tissue. Studies on athletes and exercise have shown exercise to be effective in increasing the blood volume by increasing the number of proteins and red blood cells within blood. Plasma volume has also been shown to increase after 3 weeks of high-intensity cardiovascular exercise. That is really neat. The number of proteins and red blood cells increases, so that's going to increase your blood volume. Your left ventricle is going to increase and not decrease. I'm going to write that down. And then here they're just reaffirming these 2 things are good, but the most effective thing is going to be working out. So let's use it regularly. So cardio stands for cardiovascular exercise, any exercise that raises your heart rate. This type of exercise causes the body to heat up and your heart to pump blood harder. This creates the use of more of its muscles to get nutrients to cells in need. Take a look at the following exercise devices. Select which you think will be useful in maintaining heart health. Running on the track, running on the treadmill, running on or biking on a bike. I think all these are good. I think you can't go wrong. Usually astronauts require at least 50 minutes of an hour's worth of 2 hours worth of cardiovascular, I'll just call it cardio per day. New research suggests that this may be lower depending on the technique used. Take a look at the schedule below. Based on the astronaut's exercise routine shown, what, if any, changes would you make? Here we have cardio, 10, 20, 0, 20, 0, 40, 0. Probably increase that. Wait, I would do that. Saturday looks pretty good, but probably up it on the other days. It's cool that they have to be strapped down. I want to try that out, running on a treadmill. All right, back to their favorite thing, homeostasis. Homeo meaning same, stasis, body levels. How else does exercise affect the body? Now that your astronauts have a balanced exercise schedule, they are helping the strength of their heart, but there may be other consequences. Before a workout, an astronaut's core temperature was 36.6 degrees. After the workout, it was 38. Is this astronaut falling out of homeostasis? Let's look at what homeostasis is and how it's maintained. Okay, so go ahead and define that how you would. I guess will help you out here because I'm doing the lesson. Homeostasis is the body's ability to maintain internal conditions. I want to say stable internal conditions. For example, if a person gets too hot, the body will respond with what? Sweating, which is also known as evaporative cooling. You can write maybe an example. Can you think of your own example? Thank you. we've already encountered this. We've looked at negative feedback loops. That's things getting out of balance and coming back down, getting a signal to decrease output. Insulin to decrease how you eat food, you have high glucose. Insulin lets all that glucose into the cells, decreasing blood glucose. Positive feedback loops don't necessarily maintain homeostasis. And this one, pepsin helping pepsinogen convert into more pepsin. That was a positive feedback loop. So, oh yeah, digestion. Okay, maybe that was a negative feedback loop. Oh, and we're also including positive feedback loops. Okay. How does exercise affect the body? You think homeostasis is a state or a process? A state is what something looks like at one moment, and a process is a series of steps over time. I think this is probably a process. I'm pretty confident. Body changes. To investigate this temperature fluctuation further, you measured an astronaut's core temperature continuously before and during a workout. To the right, you can see the data. Here's the time, here's the temperature. Temperature stays mostly the same before, and then during it increases over time. That looks probably something like a normal person. Wait, this one. A relaxed person to a hot, sweaty person. I mean, I guess hypothetically it could be a shivering person to a hot, sweaty person. And because the y-axis doesn't show actually what the temperature is, that's why this one could also be true, because this shivering person could become a hot, sweating person. And it's very cold in space, although I bet they keep that International Space Station at a average temperature, room temp. What advice would we give the astronaut? Exercise all the time to keep the new levels. That doesn't make any sense. Turn up the heater to 98 degrees so the environment will match to maintain homeostasis. Stick to exercise routines that has periods of exercise and periods of rest. That seems the most balanced anyway. And that's because this is dynamic. It's not the same as equilibrium. Because it's a stable process, or it's a process that fluctuates over time. And those fluctuations, or like ups and downs, can be beneficial. And why? What benefits have we discovered with exercise that could make the temperature increase worth it? So we would be increasing skeletal muscles, strengthening the heart, and strengthening bones. So it's worth it to get a little bit hot. But we can't keep it really hot for too long, so what are we going to do? So obviously don't want to stay there that long. Exercise created beneficial fluctuations, but the temperature may not have long-lasting effects. And they could have long-term physical damage if not returned. So let's look at some variables. Most of these variables would be involuntary, but for this scenario, the control is now in our hands. Predict which variables should be adjusted and in what direction to decrease the core temperature to resting levels. All right, so vasodilation. It's the widening of blood vessels, allowing more blood to flow through. I know a little something about this, so I think that will increase. The reason being, we have more surface area for temperature to diffuse out of. Heart rate pumping faster, I don't know if that will help. Bone reabsorption, what do they mean by this? It's the deterioration of bones, which increases calcium and other molecules to the bloodstream. I don't know if that's going to help either. Perspiration, it's sweating, which is excreting fluids from glands. So as that happens, it evaporates, which actually takes heat with it, something called evaporative cooling. And then I don't think blood glucose levels are really going to do anything here. So let's see, did things change when we did this? Nope. Okay, so but once we have our prediction set up, take a core measurement reading. Core, okay, current, resting, number of readings before permanent damage. Oh, we gotta figure it out. Oh, it's still too high. What heart rate would get the most blood to cooler areas? Oh, I see. So if we pump the blood faster, it would get over to cooler areas of the body, cooling it down. That's cool. We did it. Fantastic. All the variables work together. All right, what's controlled? If something can be measured is home. Oh, I'm going to take some notes on that. Okay, so this is the best way to write it down as fast as possible and in simple ways. It's getting hot in here, right? Exercise makes us hot. How do you cool down? Increased vasodilation increases the surface area and the transfer of heat. Increased heart rate, more blood to cooler areas. Increased perspiration, evaporative cooling. Sweat takes heat or energy with it when it evaporates. That's what we got. We're out of note space, so gosh, we are learning more stuff, but here we go. This looks a little bit like review because we've learned about this before. When we adjusted the core temperature, heart rate was a factor. So does that mean heart rate is homeostatically controlled? To think this out, let's first set up some terms. We'll start with the familiar homeostatic process that affects blood glucose. Match the example to its role. Okay, let's remember what's going on here. The pancreas, let's review our notes. The increase of glucose is the initial change, also known as the stimulus. And then there's a receptor or a response, and that is the pancreas is going to receive the stimulus. That's going to create the response of increased insulin, and the consequence of the effector is that pancreas B cells that. Oh wait, hold on. I think this might be. These are mixed up. So the pancreas, the B cells are going to receive the stimulus, and the glucose receptor cells will be the consequence of the effector. Okay, this is what we're looking for ultimately. We just did a take two. Let me show you. So if we have increase of glucose, that is the initial change. Then the thing that is going to receive that change, or that stimulus, is the glucose receptor cells. The pancreas B cells that secrete insulin are going to create a response, and the consequence is going to be increased insulin. Okay, and then again, this is still a high level for this 9th grade bio, but we'll do it. The stimulus is the thing that is the initial change. The receptor is the thing that receives the stimulus. The response is the created response, and the effector is the consequence. Oh wait, I think these might be mixed up. The actual response is the consequence. The effector creates the response. All right, and the terminology does help us communicate so long as we know what's going on. Okay, so then we're just doing the third step here of putting it all together. So glucose entering the bloodstream is the stimulus. We need the receptor, that's the glucose receptor cells. We have the effector, the thing that creates the response, which is the final output. The effector always throws me off, but think of it as the thing that creates the effect. All right, so if something can be measured, is it homeostatically controlled? First, what roles are connected to this example? All right, let's go through this example. We have the initial change is maybe some low blood pressure. Okay, our blood pressure goes down. Because of that, then the heart is going to receive that stimulus. Oh wait, maybe, oh, the cardiovascular center in the brain is probably going to sense that. But the heart's going to create the response, which is the consequence, which is increasing the heart rate. And let's do something like that again. So if we had low blood pressure, that is the stimulus. Or wait, low blood pressure is the initial change, the stimulus. And the cardiovascular center in the brain is going to receive the stimulus. That's going to send a message, which is going to create a response. And the effect is to increase the heart rate. The role of blood pressure is that's the stimulus, whereas the role of the heart is the effector. It's what creating the response. So blood pressure is being controlled by adjusting the heart rate. Blood pressure is then homeostatically controlled. Meanwhile, heart rate... Oh, okay, I see what it's saying. Blood pressure is not homeostatically controlled, but the heart rate is. One thing went out of whack, the blood pressure. That could have been for a number of reasons. But then the heart rate, because the blood pressure... Wait. Alright, this is confusing stuff, but here we are. The role of blood pressure is the stimulus, whereas the role of heart rate is the response. So blood pressure is being controlled by adjusting the heart rate. Blood pressure then is controlled, and heart rate is not. Overall, what is homeostatically controlled is the stimulus that is measured and reacted to. Okay, so because blood pressure was the thing that we reacted to, that's the thing being controlled by this other factor that was changed. So now what do we think? I still think homeostasis is a process. I guess not. Homeostasis, the body modulating around a regular temperature state, may not be considered a process, but is still considered homeostasis. Okay, so you can be in homeostasis, meaning you're in equilibrium, and that is a state. Oh my gosh, I can't believe that it... Of course, it is both. It's a state and a process. I didn't even really realize that was in the middle, and that makes a lot of sense. All right. Now we get to practice what we learned. Taking blood pressure here. Okay. All right. Vomiting. That seems like a dynamic process. Consistent blood pressure is homeostasis. The range in the body is going to be homeostasis. If we do an active process of removing waste, that's dynamic. And shivering or doing something, that's a dynamic process there. All right, so full picture of homeostasis. I'm going to add in here, it is also a state within the body where there is a stable internal conditions. So here in my example, if a person gets too hot, the body will respond with sweating, evaporative cooling. That's the process, and then we just added, it's a state, so the internal homeostatic state, this in a human is 98 degrees. We don't want it too hot, you don't want to be too cold either. All right, so pause and reflect. Go back and look at your notes. How well do we understand that the heart delivers oxygen systematically from the left ventricle out to the body? That's with oxygen. And that blood's ultimately going to come back through the pulmonary side, and it's going to go back up and pick up oxygen from the lungs. We got that aorta there, that arch that's carrying it. What impact does spaceflight have on the heart? So because we have lower blood volume, we have lower cardiac output, that left ventricle doesn't need to be as strong, and therefore it still can't get enough oxygen to the rest of the body, and that's not a good thing. And then we can counteract that by actually exercising. That's going to increase the walls of your heart. All right, so how to prevent cardiac atrophy. We can add on to this sentence. One thing I would do to prevent a reduction in the exercise capacity of my crew is to, I don't know, depending on your leadership style, you could say order them to exercise, or you could be like incentivize them to exercise, make it a fun game. But either way, you're getting them to exercise. So, so they can increase their heart strength, I suppose you could say, and size, keeping the heart able to pump enough blood to the rest of the body. And right, all of our cells need that oxygen in order to do ATP. Okay, and they're getting pretty fancy here. A cycle ergometer, okay, so like a bike or a treadmill, are good. We want to mention cardiovascular exercise as well. So we didn't say the specific word. I guess this is actually, it is important. So like breakdancing, if your heart rate's getting up, but maybe if you're doing yoga and you don't get that heart rate up, that wouldn't necessarily benefit your crew, although it probably helps their mental capacity. So we really want to do that cardiovascular stuff. Our turn. Reflect on what you've learned so far to modify your crew's routines. So we're going up here to this button. We're going to my mission, and we need to make their exercise plan. And I think this is where a lot of you guys are getting stuck. My mission. So let's see if I get stuck too. Here's our crew. Oh yeah, I haven't done all the stuff that you guys have done. Okay, so you should be able to go to exercise and then make sure that they are exercising enough. And especially finding exercises that have enough. Remember they said about 50 minutes of cardio every day. So maybe I change this up a little bit. I can place an X there, and I can increase. I think I'll, and then you can't really see. Oh, you could copy people's plans. For some reason, I can't get this to go down. So yeah, good luck with that. Let me know if you have any questions. making sure that each one of your crews have 50 minutes of, on average, 50 minutes a day. That's all you gotta do. And this is probably, if you guys are getting stuck here, let me know. The total points are 144. So let's put it this way. I'll give you, if you can't get that thing to work, what I'll do is have you set up your own exercise plan, which seems beneficial for you anyway. And I'll make that worth 11 points, so you can get up to the full amount. And so I'll go ahead and link that down here as well, along with some of the notes. Good job today. Yeah, we learned about the heart. I think this is a really cool postcard I picked up the other day. How can you think about the branches of this tree, which give off oxygen and collect carbon dioxide from the air? How are those similar to bringing oxygen to the heart to be pumped out to the rest of the body? And just a little bit, this is kind of cutesy and funny, but oftentimes we say the heart is the place of love. Someone posed this question to me today: what is love? So I am curious what you think. But anyway, I love all of you, and I hope you have fun doing this lesson. I know it was a kind of big lesson. It took us 46 minutes to do, and if you took some notes, maybe it took you a little bit longer. But good luck with the rest of it. I will see you all for the next lesson. And if you really enjoyed this, I suggest that you come and talk to someone who knows way more about the heart and all the things that can go wrong. He's actually my childhood neighbor, which was really fun. I just recently reconnected with him. Turns out he's going into cardiology, and he's a medical student, also in airspace. He's in the Air Force. And I was like, wow, that's really cool. And he really wants to talk to you guys. So he's going to come in Thursday morning at 10 a.m. 9 a.m. Sorry, 9 a.m. And that is all linked in the announcements. So we'll see you later. Have a good night. Take 25 and 10. That's what I'm saying. Get up, move around, dance, break dance, do some cardio, whatever you got to do. Get yourself in the mood to do another lesson of bio this week. Your penultimate lesson at this point for the penultimate week of our semester together. All right, hasta luego.